A transit of Venus across the Sun takes place when the planet Venus passes directly between the Sun and a superior planet, becoming visible against the solar disk. During a transit, Venus can be seen from Earth as a small black disk moving across the face of the Sun. The duration of such transits is usually measured in hours. A transit is similar to a solar eclipse by the Moon. While the diameter of Venus is more than 3 times that of the Moon, Venus appears smaller and travels more slowly across the face of the Sun, because it is much farther away from Earth. Transits of Venus are among the rarest of predictable astronomical phenomena. They occur in a pattern that generally repeats every 243 years, with pairs of transits 8 years apart separated by long gaps of 121.5 years and 105.5 years. The periodicity is a reflection of the fact that the orbital periods of Earth and Venus are close to 813 and 243 to 395 commensurabilities. The last transit of Venus was on 5 and 6 June 2012, and was the last Venus transit of the 21st century. The prior transit took place on 8 June 2004. The previous pair of transits were in December 1874 and December 1882. The next transits of Venus will be on 10–11 December 2117, and 8 December 2125. Venus transits are historically of great scientific importance as they were used to gain the first realistic estimates of the size of the solar system. Observations of the 1639 transit, combined with the principle of parallax, provided an estimate of the distance between the Sun and the Earth that was more accurate than any other up to the time. The 2012 transit provided scientists with a number of other research opportunities, particularly in the refinement of techniques to be used in the search for exoplanets. Conjunctions. Venus, with an orbit inclined by 3.4 degrees relative to the Earth's, usually appears to pass under the Sun at inferior conjunction. A transit occurs when Venus reaches conjunction with the Sun at or near one of its nodes, the longitude where Venus passes through the Earth's orbital plane, and appears to pass directly across the Sun. Although the inclination between these two orbital planes is only 3.4 degrees, Venus can be as far as 9.6 degrees from the Sun when viewed from the Earth at inferior conjunction. Since the angular diameter of the Sun is about half a degree, Venus may appear to pass above or below the Sun by more than 18 solar diameters during an ordinary conjunction. Sequences of transits usually repeat every 243 years. After this period of time, Venus and Earth have returned to very nearly the same point in the respective orbits. During the Earth's 243 sidereal orbital periods, which total 88,757.3 days, Venus completes 395 sidereal orbital periods of 224.701 days each, equal to 88,756.9 Earth days. This period of time corresponds to 152 synodic periods of Venus. The pattern of 105.5, 121.5 and 8 years is not the only pattern that is possible within the 243-year cycle, because of the slight mismatch between the times when the Earth and Venus arrive at the point of conjunction. Prior to 1518, the pattern of transits was 8, 113.5 and 121.5 years, and the 8 intertransit gaps before the AD 546 transit were 121.5 years apart. The current pattern will continue until 2846, when it will be replaced by a pattern of 105.5, 129.5 and 8 8 years. Thus, the 243-year cycle is relatively stable, but the number of transits and the timing within the cycle will vary over time. Since the 243 to 395 Earth-Venus commensurability is only approximate, there are different sequences of transits occurring 243 years apart, each extending for several thousand years, which are eventually replaced by other sequences. For instance, there is a series which ended in 541 BC, and the series which includes 2117 only started in AD 1631. History of observation. Ancient history. Ancient Indian, Greek, Egyptian, Babylonian and Chinese observers knew of Venus and recorded the planet's motions. The early Greek astronomers called Venus by two names, Hesperus the evening star and Phosphorus the morning star. Pythagoras is credited with realizing they were the same planet. There is no evidence that any of these cultures knew of the transits. Venus was important to ancient American civilizations, in particular for the Maya, who called it Noek, the Great Star, or Xuexec, the Wasp Star. They embodied Venus in the form of the god Kukulkan. In the Dresden Codex, the Maya charted Venice a full cycle, but despite the precise knowledge of its course, there is no mention of a transit. However, it has been proposed that frescoes found at Mayapan may contain a pictorial representation of the 12th or 13th century transits. 1639 First scientific observation. In 1627, Johannes Kepler became the first person to predict a transit of Venus, by predicting the 1631 event. His methods were not sufficiently accurate to predict that the transit would not be visible in most of Europe, and as a consequence, nobody was able to use his prediction to observe the phenomenon. The first recorded observation of a transit of Venus was made by Jeremiah Horrocks from his home at Carr House in Muchhool, near Preston in England, on the 4th of December 1639. His friend, William Crabtree, also observed this transit from Broughton, near Manchester. Kepler had predicted transits in 1631 and 1761 and a near miss in 1639. Horrocks corrected Kepler's calculation for the orbit of Venus, realized that transits of Venus would occur in pairs 8 years apart, and so predicted the transit of 1639. Although he was uncertain of the exact time, he calculated that the transit was to begin at approximately 1500. Horrocks focused the image of the Sun through a simple telescope onto a piece of paper, where the image could be safely observed. After observing for most of the day, he was lucky to see the transit as clouds obscuring the Sun cleared at about 15:15, just half an hour before sunset. Horrocks' observations allowed him to make a well-informed guess as to the size of Venus, as well as to make an estimate of the mean distance between the Earth and the Sun, the astronomical unit. He estimated that distance to be 59.4 million miles, about 2/3 of the actual distance of 93 million miles, but a more accurate figure than any suggested up to the time. The observations were not published until 1661, well after Horrocks's death. 1761 and 1769 Indiana 1663 Scottish mathematician James Gregory had suggested in his Optica Promota that observations of a transit of the planet Mercury, at widely spaced points on the surface of the Earth, could be used to calculate the solar parallax and hence the astronomical unit using triangulation. Aware of this, a young Edmund Halley made observations of such a transit on the 28th of October O.S. 1677 from St Helena, but was disappointed to find that only Richard Townley in Burnley, Lancashire had made another accurate observation of the event, whilst Gallett at Avignon simply recorded that it had occurred. Halley was not satisfied that the resulting calculation of the solar parallax at 45 inches was accurate. In a paper published in 1691, and a more refined one in 1716, he proposed that more accurate calculations could be made using measurements of a transit of Venus, although the next such event was not due until 1761. Halley died in 1742, but in 1761 numerous expeditions were made to various parts of the world so that precise observations of the transit could be made in order to make the calculations as described by Halley, an early example of international scientific collaboration. This collaboration was, however, underpinned by competition, the British, for example, being spurred to action only after they heard of French plans from Joseph Nicolas Delisle. In an attempt to observe the first transit of the pair, astronomers from Britain, Austria and France traveled to destinations around the world, including Siberia, Norway, Newfoundland and Madagascar. Most managed to observe at least part of the transit, but successful observations were made in particular by Jeremiah Dixon and Charles Mason at the Cape of Good Hope. Less successful at St. Helena were Neville Maskelyne and Robert Waddington, although they put the voyage to good use by trialing the lunar distance method of finding longitude. The existence of an atmosphere on Venus was concluded by Mikhail Lomonosov on the basis of his observation of the transit of Venus of 1761 from the Imperial Academy of Sciences of St. Petersburg. He used a two-lens achromat refractor and a weak solar filter and reported seeing a bumper bulge of light off the solar disk as Venus began to exit the Sun. Lomonosov attributed that effect to refraction of solar rays through an atmosphere. He also reported the appearance of a sliver around the part of Venus that had just entered the Sun's disk during the initial phase of transit. In 2012, Pasachov and Gian reported, based on knowing what Venus's atmosphere would look like because of Pasachov and Schneider's observations of the 2004 transit of Venus, that what Lomonosov reported was not Venus's atmosphere. To make a decisive test, a group of researchers carried out experimental reconstruction of Lomonosov's discovery of Venusian atmosphere with antique refractors during the transit of Venus on 5 to 6 June 2012. They observed the Lomonosov's arc and other aureole effects due to Venus's atmosphere and concluded that Lomonosov's telescope was fully adequate to the task of detecting the arc of light around Venus off the Sun's disk during ingress or egress. Proper experimental techniques as described by Lomonosov in his 1761 paper are employed. For the 1769 transit, scientists traveled to Tahiti, Norway, and locations in North America including Canada, New England, and San Jose del Cabo. The Czech astronomer Christian Mayer was invited by Catherine the Great to observe the transit in St. Petersburg with Anders Johann Lexell, while other members of Russian Academy of Sciences went to 8 other locations in the Russian Empire, under the general coordination of Stepan Rumovsky. The Hungarian astronomer Maximilian Hedel and his assistant Janos Sajnovics traveled to Vardø, Norway, delegated by Christian VII of Denmark. William Wales and Joseph Diamond made their observation in Hudson Bay, Canada, for the Royal Society. Observations were made by a number of groups in the British colonies in America. In Philadelphia, the American Philosophical Society erected 3 temporary observatories and appointed a committee, of which David Rittenhouse was the head. Observations were made by a group led by Dr. Benjamin West in Providence, Rhode Island, and published in 1769. The results of the various observations in the American colonies were printed in the first volume of the American Philosophical Society's Transactions, published in 1771. Comparing the North American observations, William Smith published in 1771 a best value of the solar parallax of 8.48 to 8.49 arcseconds, which corresponds to an Earth-Sun distance of 24,000 times the Earth's radius, about 3% different from the correct value. Observations were also made from Tahiti by James Cook and Charles Green at a location still known as Point Venus. This occurred on the first voyage of James Cook, after which Cook explored New Zealand and Australia. This was one of 5 expeditions organized by the Royal Society and the astronomer Royal Neville Maskelyne. Jean-Baptiste Chappedotouroche went to San José del Cabo in what was then New Spain to observe the transit with 2 Spanish astronomers. For his trouble he died in an epidemic of yellow fever shortly after completing his observations. Only 9 of 28 in the entire party returned home alive. The unfortunate Guillaume Le Gentil spent 8 years traveling in an attempt to observe either of the transits. His unsuccessful journey led to him losing his wife and possessions and being declared dead. Under the influence of the Royal Society, Ruda Boskovic traveled to Istanbul, but arrived too late. Unfortunately, it was impossible to time the exact moment of the start and end of the transit because of the phenomenon known as the black drop effect. This effect was long thought to be due to Venus' thick atmosphere, and initially it was held to be the first real evidence that Venus had an atmosphere. However, recent studies demonstrate that it is an optical effect caused by the smearing of the image of Venus by turbulence in the Earth's atmosphere or imperfections in the viewing apparatus. In 1771, using the combined 1761 and 1769 transit data, the French astronomer Jérôme Lalande calculated the astronomical unit to have a value of 153 million kilometers. The precision was less than had been hoped for because of the black drop effect, but still a considerable improvement on Horrocks calculations. Maximilian Hell published the results of his expedition in 1770 in Copenhagen, based on the results of his own expedition and of Wales and Cook. In 1772, he presented another calculation of the astronomical unit, 151.7 million kilometers. Lalande queried the accuracy and authenticity of the Hell expedition, but later he retreated in an article of Journal des Caverns in 1778. 1874 and 1882 transit observations in 1874 and 1882 allowed this value to be refined further. 3 expeditions from Germany, the United Kingdom and the United States were sent to the Kerguelen archipelago for the 1874 observations. The American astronomer Simon Newcomb combined the data from the last 4 transits, and he arrived at a value of about 149.59 million kilometers. Modern techniques, such as the use of radio telemetry from space probes, and of radar measurements of the distances to planets and asteroids in the solar system, have allowed a reasonably accurate value for the astronomical unit to be calculated to a precision of about plus or minus 30 meters. As a result, the need for parallax calculations has been superseded. 2004 and 2012, a number of scientific organizations headed by the European Southern Observatory organized a network of amateur astronomers and students to measure Earth's distance from the Sun during the transit. The participants' observations allowed a calculation of the astronomical unit of 149,608,708 kilometers plus or minus 11,800 2,835 kilometers, which had only a 0.007% difference to the accepted value. There was a good deal of interest in the 2004 transit as scientists attempted to measure the pattern of light dimming as Venus blocked out some of the Sun's light, in order to refine techniques that they hope to use in searching for extrasolar planets. Current methods of looking for planets orbiting other stars only work for a few cases. Planets that are very large, whose gravity is strong enough to wobble the star sufficiently for us to detect changes in proper motion or Doppler shift changes in radial velocity. Jupiter and Neptune-sized planets very close to their parent star whose transit causes changes in the luminosity of the star, or planets which pass in front of background stars with the planet-parent star separation comparable to the Einstein ring, and cause gravitational microlensing, measuring light intensity during the course of a transit as the planet blocks out some of the light, is potentially much more sensitive, and might be used to find smaller planets. However, extremely precise measurement is needed. For example, the transit of Venus causes the Sun's light to drop by a mere 0.001 magnitude, and the dimming produced by small extrasolar planets will be similarly tiny. The 2012 transit provided scientists numerous research opportunities as well, in particular in regard to the study of exoplanets. Research of the 2012 Venus transit includes measuring dips in a star's brightness caused by a known planet transients. The Sun will help astronomers find exoplanets. Unlike the 2004 Venus transit, the 2012 transit occurred during an active phase of the 11-year activity cycle of the Sun, and it is likely to give astronomers practice in picking up a planet's signal around a spotty, variable star. Measurements made of the apparent diameter of Venus during the transit, and comparison with its known diameter, will give scientists an idea of how to estimate exoplanet sizes. Observation made of the atmosphere of Venus simultaneously from Earth-based telescopes and from the Venus Express gives scientists a better opportunity to understand the intermediate level of Venusian atmosphere than is possible from either viewpoint alone. This will provide new information about the climate of the planet. Spectrographic data taken of the well-known atmosphere of Venus will be compared to studies of exoplanets whose atmospheres are thus far unknown. The Hubble Space Telescope, which cannot be pointed directly at the Sun, used the Moon as a mirror to study the light that had passed through the atmosphere of Venus in order to determine its composition. This will help to show whether a similar technique could be used to study exoplanets. Past and future transits. NASA maintains a catalogue of Venus transits covering the period 2000 BCE to 4000 CE. Currently, transits occur only in June or December, and the occurrence of these events slowly drifts, becoming later in the year by about 2 days every 243-year cycle. Transits usually occur in pairs, on nearly the same date 8 years apart. This is because the length of 8 Earth years is almost the same as 13 years on Venus, so every 8 years the planets are in roughly the same relative positions. This approximate conjunction usually results in a pair of transits, but it is not precise enough to produce a triplet, since Venus arrives 22 hours earlier each time. The last transit not to be part of a pair was in 1396. The next will be in 3089, in 2854. Although Venus will just miss the Sun as seen from the Earth's equator, a partial transit will be visible from some parts of the southern hemisphere. Thus, after 243 years the transits of Venus returns. The 1874 transit is a member of the 243 years cycle number 1. The 1882 transit is a member of number 2. The 2004 transit is a member of number 3 and the 2012 transit is a member of number 4. The 2117 transit is a member of number 1 and so on. However, the ascending node of the orbit of Venus moves backwards after each 243 years, so the transit of 2854 is the last member of series number 3 instead of series number 1. The descending node moves forwards, so the transit of 3705 is the last member of number 2. From -125,000 till +125,000 there are only about 10 243-year series at each of the both nodes. Regarding all the transits of Venus in this very long time span, because both nodes of the orbit of Venus moves back and forward in time as seen from the Earth, over longer periods of time, new series of transits will start and old series will end. Unlike the Saros series for lunar eclipses, it is possible for a transit series to restart after a hiatus. The transit series also vary much more in length than the Saros series. Grazing and simultaneous transits. Sometimes Venus only grazes the Sun during a transit. In this case it is possible that in some areas of the Earth a full transit can be seen, while in other regions there is only a partial transit. The last transit of this type was on the 6th of December 1631, and the next such transit will occur on the 13th of December 2611. It is also possible that a transit of Venus can be seen in some parts of the world as a partial transit, while in others Venus misses the Sun. Such a transit last occurred on the 19th of November 541 BC, and the next transit of this type will occur on the 14th of December 2854. These effects occur due to parallax. Since the size of the Earth affords different points of view with slightly different lines of sight to Venus and the Sun, it can be demonstrated by closing an eye and holding a finger in front of a smaller, more distant object. When you open the other eye and close the first, the finger will no longer be in front of the object. The simultaneous occurrence of a transit of Mercury and a transit of Venus does occur, but extremely infrequently. Such an event last occurred on the 22nd of September 373,173 BC and will next occur on the 26th of July 69,163, and again on the 29th of March 224,508. The simultaneous occurrence of a solar eclipse on a transit of Venus is currently possible, but very rare. The next solar eclipse occurring during a transit of Venus will be on the 5th of April 15,232. The last time a solar eclipse occurred during a transit of Venus was on the 1st of November 15607 BC. It could be noticed that the day after the Venusian transit of the 3rd of June 1769 there was a total solar eclipse, which was visible in Northern America, Europe and Northern Asia.